Module 2, Lesson 4, Logic Circuits. For this module, we will be covering the practical applications of your propositional logic in combinational circuit. We'll also learn how to create truth tables for compound propositional expressions. Likewise, how to implement your combinational circuit and different ways to represent propositional expressions, as well as the different steps involved in logic circuit design process. A logic circuit comprising of a set of logic gates used to represent certain propositional logic is called a combinational circuit or network. The logic gates represents an operation and the wires going through are the operands. Using the logic gates, a combinational circuit basically is roughly the analog of your formula or propositional expression, or referred to as the Boolean function. What particular propositional expression does this combinational circuit represent? Using our knowledge on the previous module regarding gates, we know that the left-hand side of your logic gates are the inputs and the right-hand side of your given logic gates are the outputs. Therefore, if I place propositional letters P and Q on this particular combinational circuit and negate P, I will end up with a negation P at this end and entering my OR logic gate along with my proposition Q, thus giving me an expression of not P or Q. This then is the truth table showing us how this particular combinational circuit works. Note that this truth table can also be used to show outcomes of complicated propositional expressions. Note that the outputs for each respective column seen on the right-hand side of your truth table reflects each connective seen on your combinational circuit. Likewise, you could also see that this expression, not P or Q, is in fact equivalent to your implication or conditional connective, which implies that this is the respective logic for your conditional or implication. What does this particular combinational circuit represent? If we place in our propositional letters at the input side of our combination circuit and evaluate through each gate, we would eventually end up with A and B, then A and B and C. And then eventually, noting that this particular combinational circuit is the representation for our 3-input AND gate. If you try to create them from 2-input AND gates, showing us the property of associativity for conjunction, as well as this is also applicable for your disjunction connective. Truth tables for different compound propositions are often constructed using the following steps. Note that a row is needed for every possible combination of values for the atomic propositions, and a column is required for your compound propositions, usually at the far right, denoting the output, and another column for the truth values of expression that occurs in the compound proposition as it is built up, which includes the atomic propositions. Let's try to construct the truth table for your propositional expression P or Q implies not R. Therefore, we'll provide a column for the 3 propositional letters P, Q, and R, serving as our input. And on the output side, on the right-hand column, we would have separate columns for each of the following connectives that are reflected on your given compound propositions, starting with not R, P or Q, and then finally, the output for P or Q implies not R. Let's try to implement then the combinational circuit for this respective expression. So we start off by evaluating P and Q, and then the output of which is connected to a disjunction OR along with your input P. And then the output of this goes to an XOR along with your input proposition R. This then is the combinational circuit for this given expression. In order to determine then how that particular expression worked and what would be its respective output for every possible value of P, Q, and R, we then show its truth table as seen on this given slide. Note that a column is provided for P and Q, and then P and Q or P, and then finally the output for the given expression P and Q or P, X or R. If we then try to implement then this propositional expression, we would then require logic ICs in order to implement then these following connectives. So we will require a 7408 for your conjunction connective, a 7432 for your disjunction connective, a 7486 for your exclusive OR connective. As seen from the previous module, in order to make this particular ICs function, you need to connect a power supply on pin 14 of these different ICs, and then pin 7 on the different grounds of these ICs. And then, of course, we utilize the pin configuration and pin assignments that are noted on the previous modules for these different ICs. Therefore, we connect your proposition P to pin 1 of the 7408 and Q on pin 2 of 7408. And then its output on pin 3 is then connected to pin 1 of your 7432. And then on pin 2 of your 7432, we connect again your input P. And then its output is now connected to your exclusive OR. On the other side of your exclusive OR, you then have your proposition R and its output seen on your pin 3. Let's try to implement then this given propositional expression and the combination circuit for this given particular expression this time. So you have not P and not Q or R. So we then negate P and then negate Q, and then or your negated Q first with your R, and then its output is connected then to an AND gate along with your negated P. This then would be your combination circuit. In order to evaluate then how it works, we simply evaluate its truth table, displaying all the possible outcomes for any possible values of P, Q, and R on your given propositional expression. In order to implement then again this given expression on a given particular circuit, we then establish again our ICs for a negation connective not 7404, an OR gate IC 7432, and a 7408 IC, an AND. And again, in order to make this particular ICs work, their pin 14s must all be connected to a 5-volt DC supply, while all pin 7s must be connected to the ground. Therefore, I connect my input proposition P on your pin 1 of your NOT gate, and its output is connected to your pin 1 of the 7408. And then I connect your input proposition Q on pin 3 of your 7404, and its output on pin 4 is connected now to pin 1 of the 7432. And then your proposition R is connected to pin 2 of your 7432, whose output is seen on pin 3 of the 7432, which is now connected to the pin 2 of 7408. And its output is now seen on pin 3 of your 7408. Note that this corresponding outputs usually shows you or indicates you if the value is 0 or 1, which implies that more often than not, we connect an LED indicator to see whether the output is 0 or 1. Likewise, your input propositions P, Q, and R are reflected as switches and are placed and connected to your respective circuit, giving us a possible input value of either 0 or 1. When representing then Boolean functions or propositional expressions, a literal is a Boolean variable or its complement. A mean term of a Boolean variable is basically the Boolean product of these different literals, where your respective yi comprises of either the value of the literal or its complement. Hence, the min term is the product of n literals, depending on how many variables are present on your given expression. The min term eventually is a product which eventually has an output value of 1. If the output value for your given min term is 0, then it's often referred to as a max term. Your min term follows what you call the sum of products expansion, whereby the sum of the min terms represents the function, which is called the sum of products expansion, which is in the disjunctive normal form of your Boolean function. The general principle is that each combination of the values of your variable for which the function has the output value of 1 requires a term in the Boolean sum that is the Boolean product of the variables or their complements. Let's then see how this particular fits into our logic circuit design process. Step 1 involves in defining the Boolean function of the operating process involved in your respective design using a logical truth table. Step 2 involves in obtaining the expression or Boolean function in mean terms using sum of products. And step 3 converts this propositional expression into a combinational circuit using the different logic gates that we've learned. Note that there are different logic circuit simulation softwares that are used in designing both the schematic and combinational circuits of your given design, as well as its actual implementation. This is one particular example. We are asked to obtain the Boolean function of a particular light bulb that operates using 2 switches such that flipping any of the switch will turn the light on when it is off, and flipping any of the switch will turn the light off when it is on. Upon doing so, we first evaluate for the different operating conditions needed for our 2 switches when turning on and off the light. Assuming that switch A is off and switch B is off, therefore our respective outcome would be no light. Now, if I flip any of this switch here, it should turn the light on. So if I flip switch A on while switch B is still off, therefore I expect there should be light. And as based from the given condition, if I flip any of this switch again, it turns the light off since the light is now currently on. So if I flip switch B this time at the on position, therefore I expect that there should be no light. Likewise, since this position has no light, therefore if I flip again any of this switch on this given condition, it should turn the light back on. Therefore, if I flip again switch A, this time at the off position, while switch B is at the on position, therefore there should be light. When converting now this particular operating process in a logical truth table, I then assign all positions of your switch at the off position to be a logic value of 0, all switch positions at the on to be a logic value of 1, all outcomes of your light bearing off to be 0, and all outcomes of your light bearing on to be 1. Therefore, we end up with this corresponding logical truth table. Your proposition letters A and B represents the 2 switches that are controlling your light bulb. And the output dictated here is your light bulb. The next step involves in deriving the propositional expression in sum of products expression or mean term. Take note, we're only concerned with outcomes bearing 1, whereby the product term for this given outcome bearing 1 would be the product of the literals A and B. But since A there is 0 and B there is 1, A there is negated and multiplied with B. Therefore, you end up with the product term A, not B. And at this given outcome, again bearing 1, we end up with the product term this time A with B. However, A there is 1 and B there is 0. Therefore, the product term would be A, B naught. If we then convert them to our sum of products expression, you would end up now with a Boolean function equal to A multiplied to not A naught multiplied to B plus A multiplied to B naught, or A naught B plus A B naught. In converting that into a particular propositional expression in which you are more familiar with, or symbols that you are more familiar with, your negation connective or not is simply replaced by a negation symbol. All multiplication symbols or multiplication operations are replaced by an and connective, and all addition or plus operations on your Boolean function is replaced by an or connective. Therefore, you'd end up now with this respective Boolean expression or propositional expression, which is not A and B or A and not B. Step 3 then designs this combinational circuit for this given expression, whereby we have our propositional letter A connected to a negation connective first, and then connected to an input of our AND gate, along with our propositional letter B. And then we get again A from the same input and connect that to another AND gate, and then use B and negate B using a NOT gate, and then place that input on the second AND gate. And then the outputs of this AND gates are joined together to your OR gate. And then the output is seen here, which eventually reflects the truth table, and the output of this particular circuit is seen or reflected by this given truth table. Circuit simulators eventually show how this combinational circuit operates, and normally displays to you the outcome as well as show you the different varying inputs that you could actually place, showing that the truth table is actually followed and observed when input values are placed on this given combinational circuit. If we then implement this particular Boolean function, I would then require a 7404, which is a NOT gate IC, a 7408, which is an AND gate IC, and a 7432, which is an OR gate IC. And remember, in order for them to operate, you need to connect all pin 14s of this IC on a 5-volt DC supply, and then all pin 7 to a particular ground. And then your input A is then connected to pin 1 of your 7404, and the output of your pin 1, which is seen on pin 2, is now connected to pin 1 of your 7408. Your input B is connected to pin 2 of the 7408, and the output of your 7408, which is on pin 3, is connected to pin 1 of your 7432. And then likewise, your input A again is connected to the second AND gate, which is seen on pin 4, while your input B is connected to your NOT gate, which is on pin 3, and the output of which is on pin 4 is now connected to pin 5 of your 7408. The output of your second AND gate, which is on pin 6, is then connected to the input of your pin 2 on your 7432, and the output of which is seen on pin 3. Let's try to implement this time a simple binary addition. We are asked to design and implement a combinational circuit that performs 1-bit addition, or often referred to as a half adder. How do we implement this? So we need to evaluate then how 1-bit addition is performed. So here I gave here an example for your 1-bit binary addition operation, whereby X is your first bit and Y is your second bit, and your C and S represents your 2-bit output. You will notice why the output becomes 2-bit. Okay, as we simulate then your respective possible input values for your binary addition by adding 0 and 0, so eventually ending up with 0, 0, or a decimal equivalent of 0. 0 plus 1, which is basically 0, 1, or a decimal value of 1, 1, 0, which is a sum of 1, which is also a decimal value of 1. And finally, you could have an input of 1, 1, whereby your respective answer should be equivalent to the binary value of 2, which is represented in terms of 2 bits now, which is 1 and 0. Notice that in order to perform this, you simply add 1 with 1, and the sum would be 0, and you carry over to the next higher power of 2 position, or the next place value of 2, your value 1. Therefore, you end up with 1, 0, which is the binary representation of your decimal 2. Hence, the outputs on your respective binary addition is depicted by a sum, which is seen on the rightmost bit or the least significant bit on your 2-bit answer, and a carry, which is seen on the most significant bit of your 2-bit answer. So when we create then the logical truth table, you would now end up with the following input values for X and Y, and the output of which is seen as carry and sum. The next step involves in obtaining the propositional expression on outcomes bearing 1 on each of your given output, which is a propositional expression for your carry and a propositional expression for your sum. The propositional expression for your carry has an output of 1 only at this given combination or Boolean product, which is X times Y, or X and Y when converted into propositional expression. Whereas for your sum, you'd end up with X not Y plus X times Y not, eventually giving us a propositional expression of not X and Y, or X and not Y. If we design then the combinational circuit for this given propositional expression that we have for both sum and carry, we would end up with an X and then negated connected to an AND gate, and your next input Y connected to the second input of your AND gate. Your X is then connected to another AND gate, your Y is then negated and is connected again to your AND gate. And the outputs of this AND gates are connected to your OR gate, which eventually represents the sum. Next, your X as well as your Y is simply connected to another AND gate. In this output, it represents then your carry. And if you simulate this combinational circuit, it should output to you this respective truth table that we previously have formed on your step 1. In designing then combinational circuits, there are several possible ways in order to design the circuit. However, you would still end up with the same respective expression, like this combinational circuit, which is also considered to be a circuit for your half adder. When we implement then these following expressions onto your logic gate ICs, we then require a 7404, a 7408, and a 7432. And again, all pin 14s of these ICs are connected to a 5 voltage supply, while all pin 7 are connected to your ground. Your X is connected to your negated NOT gate input pin 1, and then the output is connected to pin 1 of your 7408, while pin 2 of the 7408 is connected to your next input, which is your X, your Y. And then the output of this is on pin 3 is connected to your OR gate, pin 1. And then X again is connected to pin 4 of your 7408, while your Y is connected to pin 3 of your 7404 NOT gate, and its output is seen on pin 4 connected to pin 5 of your 7408. The output of your second AND gate is connected to your OR gate, pin 2 OR gate 7432, and the output of which is the sum is seen on pin 3 of your 7432. We then connect again X to another AND gate, which is seen on pin 10, and B and Y to pin 9 of our AND gate in order to determine this time the output for your carry, which is seen on pin 8. This ends Module 2, Lesson 4.